The purpose of this lab was to observe a falling tennis ball to determine the effect of gravity and drag. I extracted motion data from the video, constructed models using Newton's second law, and compared the predictions of the models with the observations. This is a clip of the tennis ball being dropped. The video was recorded at 25 frames per second and the measurements were calibrated to the diameter of the ball, which was 0.065 meters. I put the origin in the center of the ball in the first frame, just before it was dropped, and I orientated the axes so that the ball fell in the -y direction. I tracked the point masses at the center of the ball as it fell, and in the frames that the ball was blurred, I marked the center of the blur as an estimate of the position. The total observation time is 0.52 seconds, and initially the ball is moving with zero velocity. This is my model based on Newton's second law, which states that an object's acceleration depends on the net force and mass. The velocity of the ball is changing, and this suggests that the net force is not equal to zero. In my first model, I made the assumption that drag force was negligible, and that the only force acting on the ball was weight, due to the gravitational force from the Earth. I used my observations from the video to provide the initial conditions of the ball, so its initial position and velocity. I included the mass of the ball in SI units as 0.058 kilograms. I set delta t, which is the change in time, to be 0.001 seconds, as this time interval was much smaller than the time scale of the motion that I was observing. I specified the constant g to describe the magnitude of the weight force and the axis unit vector j hat to specify the direction of the weight force. Newton's second law is used here repeatedly in this loop to predict the ball's velocity and position as time advances. Since this model assumes that the system, in other words the falling ball, is being affected by only one force from the surroundings, the gravitational pull from the Earth, I have set the net force as being equal to the weight force. If we run the program, we see that the visualization seems about right. And the plot versus time also looks sensible. However, the object's motion is also affected by another interaction with the surroundings, a drag force from air resistance. I created a second model which includes both the weight and the drag force as being part of the net force on the system. All the other features remain the same, such as the initial conditions, Newton's second law, and the weight force caused by the interaction of the Earth with the object. By trial and error, I made the final position of my model be equal to the final position from my observation, and this gave me a value for the proportionality constant B to be 0.03544 Newton seconds per meter. I modeled the drag force as being in the direction opposite to the object's motion and with a magnitude proportional to the square of the object's speed. At first, the object is moving slowly, however, as the ball increases in speed, the magnitude of the drag force becomes more significant. I used a spreadsheet to compare the position data of the ball from my observation and the models. At these early times, the predicted positions are not really predictions, as I used observations from the video to set the initial conditions for the model. There is also no prediction at the end of the drag force model, as I set the constant b to make sure that the final predicted position was equal to the final observed position. In between, these model predictions of the motion, which seem generally quite reasonable. The model does seem to overpredict the motion during the in-between times. This could be due to perspective distortion because the camera may have been at an angle. Perhaps when analyzing the video in Tracker, I started observing a frame or two early, and the ball hadn't been released yet. Perhaps in the frames that the ball was blurred, I should have used a better way of estimating the position, instead of just marking the center of the blur. At the end of the observed motion, the last reading doesn't seem to fit the pattern, and it looks as though it should be lower than it actually is. And this is because at this point the ball hit the ground, and it may have begun bouncing up, which results in the anomalous result. This is a velocity time graph comparing the two models. Neither model appears to reach terminal velocity as both lines continue to slope downwards and do not reach a gradient of 0. The height of the fall of the object was quite small, so this is not surprising. If the object was thrown downwards, its terminal velocity would remain the same, as it would still have the same mass and shape. However, because it has an initial velocity, it would reach its terminal velocity quicker. The red line, which represents the velocity of the model ball, which experiences both gravity and drag, appears to have reached a gradient of 0, which indicates constant velocity, which means it has reached terminal velocity. The blue line, representing the model ball with only gravity acting on it, will remain at the same gradient forever, therefore the ball will keep accelerating at the same rate. It will never reach terminal velocity because there is no drag force to oppose the gravitational force. Thank you for listening.